You've grown up hearing that Mars is our next home, right? The obvious place we're supposed to go after the moon. Red planet, dust, rovers, bases. It's everywhere in space agency plans, in sci-fi and tech company presentations. Mars feels like the default answer before you even ask the question. And to be fair, Mars does have a lot going for it. In orbital terms, it's close. At the best alignment, Mars is about 55 million kilometers away from Earth, roughly 34 million miles. At the worst, a few 100 million kilometers. Still a long way, but within the range of a months-long mission, not a decade. The length of a Martian day is almost the same as Earth's, about 24 hours and 37 minutes, so your sleep cycle doesn't get completely wrecked. We know there's water ice at the poles and buried under the surface. We've landed multiple rovers there, driven dozens of kilometers, done drills, taken samples, and even flown a small helicopter in that extremely thin air. So Mars feels known. It feels like a hard version of a desert we already understand. But here's the problem underneath all that. Are you actually hearing Mars is best, or are you just hearing Mars is familiar? Because those are not the same thing. But before we continue, please subscribe to the channel to give your support. Let's continue. Now, let's put Titan on the table. Titan orbits Saturn. It's not a small rock. It's bigger than Mercury, about 5,150 kilometers across, roughly 3,200 miles. If Titan orbited the Sun on its own, we would absolutely call it a planet. It has a thick atmosphere, mostly nitrogen, with methane and other organic molecules mixed in. At the surface, the air pressure is around 1.5 bar. That's about 50% higher than sea level on Earth. Importantly, that means your body, from a pressure point of view, would actually be more comfortable there than on Mars, where the air is almost a vacuum. The catch is the temperature. Titan's surface is about 94 Kelvin, which is about minus 179 degrees Celsius, or around minus 290 Fahrenheit. At that temperature, water behaves like rock. Ice is not something you drink, it's something you build with. Methane and ethane, which are gases on Earth, are liquids on Titan. They fill lakes and seas. We've seen them with radar from orbit. There are rivers, channels, shorelines. It is a stable, active surface, just running on a different liquid. So on one side, you have Mars, thin air, cold rock, ice, lots of radiation, but close and familiar. On the other side, you have Titan, thick air, extreme cold, liquid hydrocarbons, possibly a warm interior, and it's much farther away. The real question you need to ask is simple. What exactly are we trying to optimize for? If the goal is speed and simplicity, get humans somewhere else as soon as possible and bring them back alive, Mars wins. Travel time is shorter, communication delays lighter, a few minutes each way instead of more than an hour. Sunlight is stronger, so solar power still works at a reasonable level. We already have a long track record of landing hardware on Mars, so the risk feels more controlled. For a quick, high-visibility mission, something like Apollo but bigger, Mars is clearly the practical choice. But if you change the goal from get there fast to build something that can last centuries, the scoring system changes. Radiation matters more. Local resources matter more. The natural chemistry of the place matters more than how pretty the sunset is. So let's look at those. Titan has one immediate advantage that is not emotional, it's physical. That thick atmosphere and its distance from the sun mean Titan's surface gets much less harmful radiation. Cosmic rays and solar storms are heavily filtered. On Mars, the atmosphere is so thin that radiation on the surface is several times what you get on Earth. There's no global magnetic field. Long-term, on Mars, you're hiding underground or you're behind very thick shielding. On Titan, the shielding is already wrapped around the whole world. That's a big deal for both humans and electronics. Next, think about chemistry. Titan is loaded with organic material. The atmosphere constantly produces complex molecules as sunlight and particles hit the methane and nitrogen. Some of that organic smog falls to the surface and piles up. The lakes and seas of methane and ethane are essentially huge pools of chemical energy. On Earth, we spend enormous effort to drill and compress hydrocarbons. On Titan, they sit there as liquid, at the surface, waiting to be pumped. If you bring or generate oxidizer, you have a gigantic natural fuel depot. Mars has ice and CO2, which you can work with known chemistry, but it's more like starting from basic ingredients and cooking everything yourself. Titan is more like walking into a kitchen where a lot of stuff is already half prepared, just at an extremely low temperature. Then there's the question of habitability versus terraformability. People like Mars because they can imagine terraforming it. It's rocky, gravity is about 0.38 g, so more than the Moon, less than Earth, but still substantial. There's some atmosphere, mostly CO2, and lots of ice. In theory, if you could dump enough energy into Mars, you could warm it up, release more CO2, thicken the air, melt some of the ice, and create liquid water on the surface. It's a gigantic engineering project, maybe impossible in practice with our current civilization, but at least the theoretical path exists. On Mars is the better target if your fantasy is turn this planet into another Earth. Titan is the better target if your plan is dig in, use what's there, and accept that the outside will always be hostile. In a way, Mars is about changing the planet to fit us. Titan is about changing ourselves and our technology to fit the environment. So that leads to the real thesis of this whole debate. The question is not, is Titan easier than Mars? You already know the answer. It's not. It's farther, colder, and harder to reach. The question you should be asking is this: if we're going to invest massive amounts of money, time, and human risk into building one deep, long-term outpost beyond Earth, should we automatically pick the place that feels familiar? Or should we seriously consider the place that might give us better radiation protection, more chemical resources, and a more interesting natural laboratory for understanding how life starts? Mars looks like the next logical step. Titan looks like the step that really tests whether we can be a spacefaring civilization, not just tourists. So the tension is simple. Do we choose the nearby world that is good for practice, or the distant world that's better for the long game? But before you can answer that, you need to deal with the brutal reality behind Titan: distance. How bad is it in actual travel time and velocity when you scale up from Mars to Saturn's orbit? And does that gap already kill the idea? So here's the blunt question now. When you stop thinking in pretty CGI and start talking hard numbers, how bad is Titan's distance really? Start with the basic layout. Earth orbits the Sun at 1 astronomical unit, about 150 million kilometers, roughly 93 million miles. Mars orbits at about 1.5 AU. So on average, it's not that much farther from the Sun than we are. Titan is riding around Saturn, which sits out at about 9 to 10 AU. That's 9 to 10 times farther from the Sun than Earth, and around 6 times farther out than Mars in terms of average orbital radius. In straight line distance along the orbit, to get to Saturn's neighborhood, you're talking roughly 1.2 to 1.7 billion kilometers, about 750 million to 1.1 billion miles. To Mars, you only need to cover tens or a few hundreds of millions of kilometers, depending on alignment. In other words, Mars is still in the inner neighborhood. Titan is out near the edge of the main system. It's not just a bit farther. Once you cross that billion-kilometer mark, everything about the mission gets heavier. More propellant, longer cruise, more time for systems to fail, more exposure to radiation in deep space, more time where you can't fix anything with a quick rescue. So the obvious next question is, how does that distance show up in something you actually feel, like travel time? With the rockets we have now, or anything close to them, Mars missions use what's called a Hohmann transfer, a kind of efficient elliptical path between orbits. That gives you a cruise time on the order of 6 to 9 months to get from Earth to Mars. Long, yes, but still inside one normal mission cycle. You can load a spacecraft with life support, food, and spare parts for that duration, and it's painful but manageable. Now compare that to Saturn's orbit. When we sent the Cassini spacecraft, it took about 7 years to get there. Not because the engines were weak, but because you trade time for fuel efficiency and use gravity assist to bend your path. NASA's Dragonfly mission to Titan is planned on a similar timeline: launch late in the decade, arrival around 2034. Again, roughly 7 years of cruise. That's not a small difference. You go from less than a year to most of a decade just to arrive. For robots, 7 years is annoying but fine if you design for it. For humans, 7 years in transit is brutal. You have to carry food, water, radiation shielding, and spare hardware for that entire time. And then you still need resources to actually live and work at the destination. Every extra year in deep space multiplies the mass and cost of the mission. So the next layer of the problem is obvious. If the distances explode, what happens to the speed changes you need to even pull this off? The thing engineers call delta V. Delta V, is just a clean term for how much you need to change your spacecraft's velocity over the whole mission. It's the total speed budget. From low Earth orbit out to a transfer orbit to Mars, you need something like 3.6 kilometers per second of extra velocity beyond what it took to reach low Earth orbit in the first place. To get onto a path to Saturn and then match orbits in that region, you're looking at more like 6 kilometers per second beyond low Earth orbit, depending on the exact trajectory and how many gravity assists you use. That jump from roughly 3.6 to roughly 6 kilometers per second doesn't look huge, but rockets don't care about how it looks. They care about the rocket equation. As you push delta V higher, the amount of propellant you need rises exponentially compared to your payload mass. A small increase in required speed turns into a large increase in fuel mass, which means a much bigger launch vehicle or a much smaller payload, or both. In simple terms, going from Mars-class missions to Titan-class missions pushes you into a much harsher trade space. You're either flying lighter, more fragile payloads, or you're stacking up bigger and more expensive rockets on the launch pad. And there's another consequence of that higher delta V that's easy to ignore. The more energy you put into the trajectory, the harder it is to change your mind later. Which leads straight to the next uncomfortable question. What does this do to your flexibility, your launch timing, and your ability to abort if something goes wrong? For Mars, the basic launch window rolls around about every 26 months when Earth and Mars line up in a way that makes the transfer efficient. Miss one window, you wait a bit over 2 years and try again. The trajectories are still complex, but the pattern is regular, and you can plan a sequence of missions, one after another, using that rhythm. On top of that, because Mars is relatively close, you can design some trajectories with possible free return or abort options, paths that loop back toward Earth if you have a major failure early on. It's not simple, and it's not like turning a car around, but at least you can talk about it seriously. With Titan, you lose most of that comfort. Launch windows are more constrained by planetary alignments, gravity assists, and the need to hit a very specific target in Saturn's huge orbital neighborhood. If you miss a Titan-class window, you might delay by many years, not just one cycle. And once you're on your way, you're on a multi-year deep space arc. There is no fast slingshot home that gets you back in a few months. If something fails halfway out, your crew is still years from any safe harbor in either direction. That makes crewed Titan missions with our current or near-term technology almost absurdly risky. Realistically, you send uncrewed probes first, then more, then maybe crewed missions far in the future, after we have much better propulsion and life support systems. So the situation narrows down to a tough trade. Is any destination worth that kind of commitment, where distance and delta V lock you into a one-way, multi-year path with no good escape route? If your horizon is one human lifetime, Mars looks much more attractive. You can fly many missions, learn from failures, build up experience. Titan, by comparison, looks like a once-in-a-generation shot each time you go. But if you start thinking in terms of civilization-scale goals, the calculus can shift. If Titan really does offer far better radiation shielding, massive hydrocarbon resources, and a unique window into how life might start in a completely different environment, a future, more advanced civilization might decide that the extra years and the harsher delta V are a price worth paying. In that frame, going to Titan with people is less like sending an expedition and more like committing to a permanent generational outpost, where coming back is not the main goal. That's a very different mindset from visit Mars and return with samples. But even if you accept that distance and that lack of an easy abort, there's another hard question waiting for you. When you finally arrive at one of these worlds, do you want almost no air like Mars or a thick, crushingly cold atmosphere like Titan? So after thinking about how far these worlds are, here's the next hard question. When you finally arrive, do you want almost no air like Mars or a thick, crushingly cold atmosphere like Titan? Start with Mars because it sounds simple, but it really isn't. Mars's atmosphere is mostly carbon dioxide, about 95%. But the key thing is pressure. At the surface, it's around 0.6 kilopascals. Earth at sea level is 101 kilopascals. So Mars is well under 1% of Earth's surface pressure. That's so thin that it's basically a vacuum from your body's point of view. If you stepped outside a habitat on Mars without a pressure suit, you wouldn't just get cold. The low pressure would make the water in your blood and tissues start to boil away. Your saliva would bubble, your lungs couldn't hold air, and you'd lose consciousness in seconds. This is why every Mars suit has to be a full pressure suit, not just a warm coat with an oxygen line. That ultra-thin air also changes how the planet behaves. Those famous dust storms that cover whole continents look terrifying, but because the air is so thin, the force on your body is more like a persistent light sandblasting than a hurricane. The grains can damage equipment over time, scratch lenses, and cover solar panels, but they don't slam into you with the kind of push a storm on Earth does. So Mars gives you almost none of the benefits of an atmosphere, like protection and lift, but still gives you problems like dust and temperature swings. It's the worst of both worlds in a very specific way. So if Mars is basically a near vacuum with some dust mixed in, does Titan actually help you, or is it just a thicker way to die? Titan's atmosphere looks surprisingly familiar on paper. It's mostly nitrogen, roughly 95%, just like Earth's, plus around 5% methane and small amounts of other organic molecules. The surface pressure is about 1.5 bar, so around 1.5 times Earth's sea level pressure. In everyday terms, that's like standing 5 to 10 meters underwater on Earth, maybe 15 to 30 feet. Your body can handle that kind of pressure very well. The problem is not the pressure, it's the temperature and the chemistry. At Titan's surface temperature, around 94 Kelvin, the air is lethally cold. Any exposed part of you would freeze solid very quickly. You also can't breathe the air. There is no oxygen for your lungs. But here's the key difference from Mars. In principle, if you had a really good thermal suit to keep you warm and a breathing system to give you oxygen, you wouldn't need a full high-pressure suit. The outside pressure is already in the right ballpark for your blood and organs. That means lighter suits, simpler seals, and less mechanical stress on your body, once you solve the heating problem. From a pure pressure standpoint, Titan's atmosphere works with your biology. Mars's atmosphere does not. So if Titan's air matches your body's needs on pressure, what does that mean for the one thing you can't see, but that hits you every second out there? Radiation. This is where Titan starts to look like a fortress, and Mars looks like a glass house. On Mars, there is almost no global magnetic field, and the thin atmosphere blocks very little high-energy radiation. Measurements from landers and rovers show surface radiation doses in the range of a few hundred microsieverts per day, several times higher than what you get on Earth at sea level. Over a long stay, that adds up to a serious cancer and tissue damage risk. For a permanent habitat, you're talking about burying habitats under meters of regolith or building them into cliffs and lava tubes, just to get back to something like Earth's protection level. Titan stacks several advantages at once. First, that thick atmosphere absorbs a lot of cosmic rays and solar energetic particles before they ever reach the ground. Second, Titan is much farther from the sun, so the intensity of solar radiation is already weaker. Third, Titan sits inside Saturn's broader magnetic spheric environment for part of its orbit, which can help deflect charged particles. Put all of that together, and you get a surface that is far less hostile in terms of radiation. So while Mars forces you to build heavy shielding and hide underground, Titan hands you a natural radiation barrier for free, wrapped around the whole world. But atmosphere doesn't just matter as a shield, it also drives weather. So which world actually gives you weather you can live and work with? On Mars, weather is simple but harsh. You get thin CO2 clouds, occasional local dust devils, and sometimes global dust storms that can last for weeks or months. Because the air is so thin, those storms don't knock over buildings, but they do block sunlight and cover everything in dust. Temperatures can swing more than 100 degrees Celsius between day and night. That's more than 180 degrees Fahrenheit. You might see a mild afternoon near 20 degrees Celsius, about 70 Fahrenheit, and then a night that drops below minus 100 Celsius, around minus 148 Fahrenheit. Any surface system has to handle those swings without breaking. Titan's weather is different. There, methane takes the role that water has on Earth. You have methane and ethane evaporating from lakes and seas, forming clouds and then raining back down as liquid hydrocarbons. Cassini's radar mapped real lakes and seas near the poles, some larger than the Great Lakes on Earth. The Huygens probe saw channels and features that look like they were carved by flowing liquids. So Titan has a full cycle: evaporation, condensation, rain, rivers, and seas, just using methane instead of water. From a science point of view, that's incredibly valuable. From an engineering point of view, it means your base might have to deal with wet, slick ground, possible flooding, and changing surface conditions, but at least it's a stable, predictable fluid cycle, not random chaos. Once you understand the air and the weather, you hit the next practical issue. Does that atmosphere make landing and flying easier, or does it just give you new ways to crash? For Mars, thin air ruins both entry and flight in a very specific way. When a spacecraft hits the atmosphere at several kilometers per second, there is enough air to heat the heat shield to insane temperatures, but not enough air density to slow you down gently with parachutes alone. That's why missions like Curiosity and Perseverance needed complicated sequences: heat shields, supersonic parachutes, then rocket-powered descent stages, basically sky cranes, to lower the rover safely. Parachutes don't bite hard enough in that thin air. Rockets have to do a lot of extra work, and your timing and guidance margins are tight. Flying in that air is also hard, as the Ingenuity helicopter showed. You need very large rotors spinning very fast just to get enough lift for a tiny mass. Flip those constraints. When Huygens entered Titan's atmosphere, it took over 2 hours to fall from the upper atmosphere to the surface under a parachute. The air is dense enough that parachutes work extremely well. You still get serious heating during entry because you're moving fast, but the deceleration is spread over a longer time and thicker air. Once you're down, flying becomes much easier. Titan's gravity is about 0.14 g, roughly 14% of Earth's, and the air is thick. That combination means even relatively small rotorcraft can lift significant payloads at low airspeeds. That's exactly why Dragonfly is a flying lander, not a wheeled rover. On Titan, it is actually simpler and more efficient to hop by air from one side to another than to drive across the ground. So from an atmosphere point of view, Mars is almost a vacuum that forces you into complex, high-risk landing systems and makes flight barely possible. Titan gives you pressure your body can tolerate with the right suit, strong radiation shielding, an active weather cycle, and air that makes both landing and flying much easier once you've handled the cold. But even if Titan's air looks better on paper, there's another big physical constraint you can't dodge: gravity. How much gravity do you actually want pulling on your bones every day? 0.38 g on dusty Mars or 0.14 g on frozen Titan? And what does that do to your body over years? So here's the next uncomfortable question. When you live somewhere for years, do you actually want Mars's medium gravity or Titan's barely there pull on your body? On Mars, surface gravity is about 3.71 meters per second squared, roughly 0.38 g. That means you weigh a bit more than 1/3 of what you do on Earth. You don't float away, you still walk, you can still fall, but every step would feel lighter. Every jump would carry you farther. That sounds fun for a week. The real issue is what happens after 5 years or 20. We know what zero-G does on the International Space Station. Astronauts lose bone density, their muscles weaken, their hearts and blood vessels adapt to not pushing against gravity, and they need heavy exercise every day just to slow that down. We have almost no direct data on 0.38G. It's probably better than 0G, but we don't know if it's good enough for a healthy lifetime. Your skeleton evolved under 1G. Put it under 0.38G for decades and it may still slowly lose mass. Your spine may change shape. Your heart may remodel in strange ways. Maybe exercise can fix it, maybe not. You would be running a huge medical experiment on the first colonists. So Mars looks like a compromise. Not full gravity, not microgravity. That leads to a simple question. If 0.38G is an unknown, what does it mean when you go even lower, to Titan's gravity? Titan's surface gravity is about 1.35 meters per second squared, roughly 0.14G. That's lower than the Moon, which is around 0.16 to 0.17G. On Titan, you would weigh about 1/7 of your Earth weight. If you're 70 kilograms on Earth, you'd feel like 10 kilograms there. From a movement point of view, you'd be able to make very big, slow jumps. With a thick atmosphere, in theory, you could strap on wings and get lift with your own muscles. That sounds cool on video, but your body doesn't care about the visuals, it cares about load. At 0.14G, your bones and muscles would be under very low stress. Over time, that probably means much faster loss of bone density than on Mars, and maybe even faster than on a station, depending on how your body responds to the constant but tiny load. Your inner gear and balance system would also have to adapt to a strange in-between state. Not floating, not anchored. We have almost no data on how organs behave under that level of gravity for decades. The honest answer is, Titan's gravity is a medical black box. It might be manageable with intense training and technology, or it might be so damaging that normal humans simply can't live there long-term without major augmentation. So if Titan is worse for your body but better for your fuel tanks and structures, how much do you care about gravity when you start building large habitats and infrastructure? For engineers, lower gravity is helpful. Structural loads scale down. A dome that is pushing the limit on Earth under 1G would be far below its stress limit on Titan. On Mars, you still have to think seriously about how much weight your beams and arches are carrying. On Titan, that same design would be overbuilt, which gives you safety margin. That matters if you want to use local water ice as a building material. At Titan temperatures, ice behaves like rock. In 0.14G, huge ice blocks can support impressive shapes without collapsing. You can build larger spans, thinner walls, and taller towers with the same material strength. That doesn't mean Mars is bad. Mars gravity is still low enough that you get some structural benefit. A habitat that would need heavy steel support on Earth could use lighter materials on Mars, especially if it's partially buried in regolith for radiation shielding. But Titan really lets you push this to another level. For robots and static structures, Titan's low gravity is an advantage. For human bones and hearts, it's a risk. Then you get into the practical side of actually moving stuff around. How does gravity change mobility and logistics on each world? On Mars, we've already had rovers like Spirit, Opportunity, Curiosity, and Perseverance rolling around. Their top speeds are on the order of centimeters per second to maybe a few tens of centimeters per second, so a fraction of a kilometer per hour. Because careful driving and navigation matter more than raw speed. Mars's 0.38G is enough that wheels have good traction, and heavy equipment can be anchored to the ground without drifting. But you're still fighting slopes, rocks, and dust. Any large cargo has to be hauled by relatively conventional vehicles. On Titan, 0.14G and a thick atmosphere open up completely different options. Rotorcraft like Dragonfly can cruise at a few meters per second, like a slow bicycle, but hop tens of kilometers between landing sites in one Titan day. Now scale that concept up. In principle, you could have big, slow cargo blimps or rotorcraft lifting tens of tons of equipment with the power a small truck engine uses on Earth. You don't need fast airspeed because the air is dense and gravity is weak. Moving heavy gear by air may actually be easier and more energy efficient than dragging it across the ground, especially if the surface is soft hydrocarbons and ice grains. So, Titan's low gravity and thick air make robots extremely mobile. They turn the whole moon into a three-dimensional logistic zone. Mars, by contrast, keeps you mostly on the ground, with careful rover paths and maybe small helicopters assisting. From a logistics standpoint, Titan is much more flexible once you get there. All of this brings us back to the core human problem. What are you really trying to support? Life support systems or the human body itself? On Mars, the main fight is life support. You have to give people air, pressure, heat, water, and radiation shielding. But the gravity might be just high enough that your skeleton and muscles can function with heavy exercise and medical help. You design habitats, but you're at least somewhat confident the human frame can adapt to 0.38 G. So Mars becomes the body compromise. Not perfect, but possibly workable for multi-year stays. On Titan, you inherit a much harder challenge. You still need all the life support tech, plus extra heating because it's cryogenic outside. On top of that, your body is in a gravity regime that might be fundamentally unhealthy for long-term human biology. Titan looks excellent for robots. They don't care about gravity, they benefit from lower structural loads, and they can fly and float easily. For humans, Titan probably belongs to a later phase, when we have the ability to modify ourselves or build exoskeletons and artificial gravity habitats that handle the health side. So if Mars is where you test whether ordinary humans can live off-world with strong but normal technology, Titan is more like a lab for advanced robots and future humans with serious augmentation. One is trying to keep you close to your current biology, the other is forcing you to push past it. But even if you solve all of that, your heart, your bones, your logistics, you still run into another cold limit: energy. In a place where sunlight falls to a fraction of Earth's, which world actually gives you the better long-term power deal? Dusty Mars with weak but usable sunlight, or frozen Titan with almost no light but huge stores of chemical energy? Here's the next hard question you have to answer before anything else. Where does the power come from every hour, every day on Mars and on Titan? Start with Mars, because this is the one that sounds simple. We'll just use solar panels. At Mars's distance from the sun, the sunlight is roughly 43% of what Earth gets. So if you have a solar array that delivers 1 kilowatt on Earth under good midday sun, you're looking at maybe 400 to 450 watts on Mars, before you even talk about dust. That's already a big downgrade. Now add in reality. Dust slowly settles on the panels. Occasionally, you get regional or even global dust storms that dim the light for days or weeks. Your 400 watts can drop to a fraction of that. Rovers like Opportunity and Perseverance showed that this is still workable, but only with very careful design, smart power management, and a bit of luck, like gusts of wind cleaning off the panels for free. For a small rover, a few hundred watts can run electronics and motors. For a base with people, heating, air recycling, water processing, and industry, those numbers start to look tight very fast. So yes, Mars supports solar, but you're always fighting the numbers. You need more area, more cleaning systems, more batteries, and backup power for bad seasons. That leads straight to the next question. If Mars is already this marginal on sunlight, what happens when you go all the way out to Titan? On Titan, daylight basically collapses. At Saturn's orbit, the raw sunlight is about 1% of what Earth gets. Then Titan's thick, hazy atmosphere knocks out roughly 90% of that before it reaches the ground. So at the surface, you're left with around 0.1% of Earth's sunlight. Put that in simple terms. Let's say you have a solar setup on Earth that gives you 1 kilowatt on a clear day, something like a decent-sized rooftop array. Take that same area, same technology, and drop it on Titan's surface. You're now getting about 1 watt. That's the power draw of a tiny LED, not a habitat. You can't fix this by saying, we'll just add more panels. To get the same 1 kilowatt you had on Earth, you'd need roughly 1,000 times more area, and that's before you account for snow-like hydrocarbon deposits building up on the panels, or mechanical issues in that extreme cold. The mass, complexity, and maintenance load explode. Solar becomes something you use for small instruments or emergency backup, not a primary grid. So Titan forces you into a corner, and the question becomes very sharp. If sunlight is basically gone, what kind of power source are you actually betting on? That's where nuclear stops being nice to have and becomes mandatory. On Mars, nuclear reactors and radioisotope generators are a strong option because they ignore dust and night. On Titan, they're the only serious option for large-scale power. NASA's Dragonfly mission will run on an MMRTG, a radioisotope generator using plutonium-238. It will provide tens of watts of electrical power continuously, plus waste heat that helps keep systems warm. That's enough for a robot the size of a car to fly, land, and run instruments if you manage power very carefully. Now scale up to a human outpost. You're not talking tens of watts, you're talking megawatts. You need power to keep habitats at livable temperatures, to run life support systems, to crack water ice into hydrogen and oxygen, to refine hydrocarbons, to recycle air and water, and to do any kind of heavy industry. That means real fission reactors, shielded, maintained, and probably built with a lot of redundancy. And because Titan is so cold, the waste heat from those reactors isn't just a nuisance, it's part of your thermal management plan. You're using that heat to keep equipment from freezing solid and to warm living spaces. On Mars, you could, in theory, run an early base mostly on solar with some nuclear backup, then add reactors later. On Titan, you don't even start without nuclear, so you're forced to ask a blunt question. If sunlight is basically gone, what kind of power source are you actually betting on? But nuclear is only half the story. There's a twist in Titan's favor that's easy to miss if you only stare at sunlight charts. How much does it help you that Titan is basically sitting on a giant pile of chemical fuel? Titan's surface is dotted with lakes and seas of liquid methane and ethane. The atmosphere is thick with nitrogen. From an energy perspective, that is an enormous resource. On Earth, natural gas fields are buried underground, under rock, under high pressure. You spend a lot of energy finding them, drilling into them, and bringing the gas to the surface. On Titan, the methane and ethane are already there, at the surface in liquid form. You can pump them like oil. You still have to refine, store, and handle them in extreme cold, but the basic step of get the fuel is much easier. The missing piece is oxidizer. To burn methane for energy or to use it as fuel for rockets, you need oxygen or something similar. On Titan, there's essentially no free oxygen in the atmosphere. You either import oxidizer from somewhere else, or you crack water ice in the crust and subsurface into hydrogen and oxygen using your nuclear power. That takes energy, but once you have a steady supply of oxygen, the combination of local hydrocarbons and produced oxidizer gives you a very powerful chemical energy loop. You can run power plants, fuel vehicles, and store energy in fuel tanks rather than only in batteries. Compare that to Mars. Mars has CO2 and water ice. You can make methane and oxygen there using industrial chemistry, reacting CO2 with imported or locally produced hydrogen and splitting water. It's absolutely doable, but you're building the fuel from more basic ingredients. On Titan, the carbon and hydrogen are already combined into energy-rich molecules, waiting to be tapped. So now you can see the energy trade in cleaner terms. Mars gives you a more comfortable start. You get weaker but still usable sunlight. You can land a mission that mostly runs on solar arrays and batteries, with maybe a small nuclear unit for backup, and then add reactors and more infrastructure. Titan gives you almost no solar path at all, but it hands you massive chemical resources to exploit once you have reactors in place. That sets up the big question you have to answer for the long run. Which phase of the game do you care about more, the early bootstrapping or the late-stage industrial expansion? If your goal is to get something working in the next couple of decades, Mars wins. You can launch with tech we already understand, scale up solar, and add nuclear as we go. Titan is brutal at the start because nuclear is non-negotiable and every system has to handle cryogenic conditions. But if you think in centuries, Titan's combination of hydrocarbons, nitrogen, and potential water ice makes it an energy-rich world once your initial infrastructure is online. And remember, those hydrocarbons aren't only fuel, they're also clues. The same chemistry that makes Titan good for energy makes it a perfect lab for studying complex organic processes and the steps toward life. So the tension gets sharper. Are we treating Titan as a future fuel depot or as a unique laboratory where we should be very careful about what we burn? Because that brings us straight to the next level of the argument. Not just power, but chemistry. Which world really gives you the better chance to understand how life starts? The dry, oxidized soil of Mars or the cold alien seas and atmosphere chemistry of Titan? Here's the blunt question now. If you really care about finding out how life starts, where do you go first? The dry dirt of Mars or the alien lakes of Titan? Let's be clear about one thing up front. Titan's methane lakes are not theory. They're not concept art. They're real, measured. Cassini used radar to map Titan's poles, and it found real lakes and seas, some hundreds of kilometers across, some of them rivaling or exceeding the Great Lakes in area. These are bodies of liquid sitting on the surface, not buried pockets. The liquid is mostly methane and ethane, which only stay liquid because Titan's surface sits down at about 94 Kelvin, around negative 179 degrees Celsius, or negative 290 Fahrenheit, and the pressure is about 1.5 bar. In that range, methane behaves the way water does on Earth, stable as a liquid under an atmosphere. We've seen shorelines, we've seen shapes that look like bays and peninsulas, we've picked up hints of waves, and we've observed patterns that match rainfall and drainage. Huygens, during its descent, saw features that matched channels carved by flowing liquid. So when we say seas of methane, it's not poetic, it's literal. Titan is running a full liquid cycle on its surface, just in a different chemical regime. So if Titan has real alien seas, what does that actually do to the chemistry, and why does it matter to you sitting here on Earth? On Earth, you learn a simple rule in school. Like dissolves like. Polar molecules mix with polar molecules, nonpolar with nonpolar, water and oil don't mix, end of story. Titan's environment pushes that rule until it starts to bend. Lab experiments and models suggest that under Titan-like conditions, very cold, moderate pressure, some polar molecules and non-polar hydrocarbons can form stable mixed structures, things like co-crystals. Hydrogen cyanide, HCN, which is a polar molecule and important in many prebiotic chemistry scenarios, appears able to combine with methane and ethane in these conditions. That means you can get complex structures where on Earth you'd expect separation. You might have solid lattices that trap both water-related compounds and hydrocarbon-related compounds together. That opens up reaction pathways we don't even have standard names for, because our chemistry experience is all at room temperature in water. On Titan, the solvent is a very cold hydrocarbon, and the rules of what can meet what and how are different. So now the question turns into this. Are we looking for life that just copies Earth's chemistry, or are we trying to find out if life can start in totally different conditions? Titan gives you a very clean test. Its atmosphere is a mix of nitrogen and methane, with a thick organic haze, which actually looks a lot like some models of early Earth's atmosphere before oxygen built up. The key difference is the environment where the chemistry runs. Early Earth probably did most of its prebiotic work in liquid water at roughly 300 Kelvin, around room temperature. Titan is doing its chemistry at about 94 Kelvin, with liquid hydrocarbons as the main solvent. In both cases, you're dealing with the same basic elements: carbon, hydrogen, nitrogen, and some oxygen and other elements in smaller amounts. But the solvent, the temperature, and the reaction rates are completely different. If life, or something very close to life, can start in both settings, that strongly suggests that chemistry is flexible, that the universe might be full of paths to biology, not just one special route through warm oceans like Earth's. Titan is basically running a parallel version of the "how does complexity arise out of simple molecules" experiment. Put that next to Mars, and the contrast is pretty harsh. Mars absolutely has interesting chemistry. You have perchlorates in the soil, which are reactive chlorine-based salts. You have possible subsurface brines, and you have a lot of variation in minerals and rock types. But at the surface, today, Mars is dry, cold, and oxidizing. There's thin atmosphere, lots of ultraviolet radiation, and plenty of cosmic rays. Any organic molecules near the surface get broken apart over time. If Mars ever had rich organic chemistry, it was probably billions of years ago, when it had thicker air and stable liquid water on the surface. That means Mars is great if you're hunting for fossils, for preserved signs of past life, or stable organics locked in rocks and buried ice. But the surface environment now is more like a cleanup crew than a chemistry factory. It tends to destroy complex molecules, not create new ones. Titan, in contrast, has an atmosphere that continuously generates new organics as sunlight and particles hit the methane and nitrogen, building complex haze and depositing it onto the surface and into lakes. The chemistry engine is running now, not only in the distant past. So if Mars is a crime scene from a very old case, Titan is an active lab where the experiment is still going. That leads directly to the next point. If you want to understand that experiment, you don't just send a lander, you send a machine that can move, sample, and compare. That's where Dragonfly comes in. Dragonfly is not a simple lander, it's a rotorcraft specifically designed for Titan's low gravity and dense air. It will be able to lift off, fly a few meters per second, and hop tens of kilometers from one location to another between Titan days. Every time it lands, it can sample the surface, drill a little, and run the material through its instruments. It will carry tools like mass spectrometers to identify molecules, gamma ray and neutron instruments to probe what lies just below the surface, and full meteorology packages to track weather and atmospheric chemistry. The mission plan focuses on different types of terrain. Dunes made of organic grains, areas where impacts may have melted water ice and mixed it with organics, places where liquids might have flowed and then evaporated. In each place, Dragonfly will be looking for patterns, stepwise increases in molecular complexity, hints of structures that behave in lifelike ways, like self-organization, energy use, or information storage, even if they're not life as we define it. If you go to Titan and find complex, life-adjacent chemistry that clearly evolves separately from Earth's path, that is a direct hit on the idea that life is a rare accident. It suggests that whenever you have carbon, nitrogen, energy, and time, chemistry leans toward complexity. That doesn't prove life is everywhere, but it makes it much harder to argue that Earth is a one-off miracle. And that's where the tension spikes. Titan might be both a future energy resource and a unique natural lab for prebiotic chemistry. Every drill core you burn as fuel could be a sample you never get to analyze. Every refinery you build on a shoreline might overwrite chemical traces that took millions of years to form. So now the question is not just where can we live, but what are we willing to disturb in the name of that life? Because chemistry on the surface is only half of Titan's story. Under the crust, things might get even stranger, with slushy ice, pockets of liquid water, and hidden environments that are closer to what microbes like on Earth. So the next issue is simple and uncomfortable. If Titan's surface is already this interesting, what exactly is going on in the dark under hundreds of kilometers of ice? You'd think the story with Titan's interior would be simple. Frozen shell on top, big warm ocean underneath, case closed. It looked that way for years. Cassini measured how Titan wobbled and how Saturn's gravity tugged on it, and the data fit a neat picture: a solid ice crust floating on a deep global subsurface ocean of liquid water. That put Titan in the same category as Europa and Enceladus, the ocean worlds everyone talks about when they talk about hidden seas and alien microbes. In that old model, you had a thick ice lid, maybe tens of kilometers, then a deep world ocean wrapping all the way around the moon. It was easy to picture, like a planetary-scale water tank with a frozen roof. If that were true, the question for life becomes straightforward. Is there any energy moving through that water, any chemistry at the seafloor, and any mixing between the ocean and the surface? Titan looked like a prime candidate for life under the ice, on top of everything already happening in the atmosphere and at the surface. But then the numbers got pushed harder and the simple story started to crack. So the next thing you have to ask is, what if Titan isn't a clean ocean world at all, but something messier? More recent reanalysis of Cassini's tracking data and gravity measurements suggests Titan might be stiffer than people first thought. It doesn't flex as easily under Saturn's tides as a thin crust over a deep global ocean would. That hints that the interior might not be one big continuous liquid layer. Instead, you might be looking at thick, high-pressure ice near its melting point, with pockets and channels of liquid water and water-ammonia mixtures threaded through it. Picture it less like an Atlantic Ocean under ice and more like a planet-sized sponge, a network of slushy tunnels and brine pockets extending through the deep interior. Some models even suggest that in certain regions, under the right pressure and composition, that water could reach temperatures around 20 degrees Celsius, about 68 Fahrenheit. That's not just not frozen, that's squarely in the comfortable range for life as we know it. So the environment might be patchy, but locally surprisingly warm. So now, habitability on Titan stops being a one-layer question. You're not just asking, is there an ocean? You're asking, how much slush is there, how connected is it, and how long does it stay active? That pushes you into a different way of thinking about where life could survive. Instead of imagining big open seas, you think in terms of porous, convecting ice filled with brines, maybe mixed with ammonia, maybe carrying salts and organic materials. On Earth, you already see this in a small way. In polar regions, inside sea ice, there are brine channels, tiny liquid tubes that stay unfrozen because the salt content depresses the freezing point. Microbes live in those channels, in a place that from the outside looks absolutely dead. Now scale that up. Titan could be running a whole version of that inside a moon. You have solid ice that, under the microscope, is full of slushy networks. Water and ammonia move, nutrients migrate, and temperature gradients exist. Those are all things life likes. The habitat doesn't have to be a giant open ocean. It just has to be stable, chemically interesting, and persistent for long spans of time. So if Titan has this deep, cushioned, long-lived slush layer, how does that stack up against what's hiding under Mars? Mars almost certainly has ice in the subsurface across large areas. Radar data from orbit and neutron measurements point to buried ice sheets and mixed ice-dust layers. There are hints of briny water films or small brine pockets, especially near the poles or in certain salt-rich terrains. There might even be isolated aquifers, pockets of liquid water kept from freezing by salt and pressure. Those are all interesting from a life perspective. But here's the key difference. Mars's subsurface is shallow compared to Titan's. You're dealing with layers that are maybe meters to a few kilometers down, much closer to the surface and much more exposed to long-term cooling and surface-level radiation effects. The environment can change with climate shifts, obliquity changes, and surface processes over millions of years. Liquid pockets there might be temporary, appearing and disappearing as conditions fluctuate. Titan's suspected slush layers sit tens to hundreds of kilometers below the surface, buried under a thick ice shell. They are insulated from space, from radiation, from quick climate swings. The heat budget is driven more by radioactive decay in the core and long-term tidal effects than by surface weather. That makes those slushy regions potentially more stable over geological timescales. You're not just comparing liquid versus ice. You're comparing shallow, possibly short-lived wet spots on Mars with deep, buffered reservoirs on Titan that could stay active for billions of years. So the tension becomes sharper. Do you bet on a world where water is easier to reach but maybe more fragile in time, or on a world where water is buried and hard to access, but may be stable for much longer? The honest answer is, we don't know yet, and that's exactly why the next wave of missions matters so much. Titan's Dragonfly mission isn't a dedicated ocean probe. It's a surface and near-surface explorer. But even from the surface, it can help. The composition of rocks and ices, the ratio of certain elements and isotopes, and the distribution of geological features can all hint at what's happening deep below. If Dragonfly finds clear signs of materials that must have been processed in a warm interior and then brought up, that strengthens the case for active slush systems and internal cycling. On Mars, we've already had a seismometer with the InSight lander, listening to Mars quakes and impacts. Those measurements plus ground-penetrating radar from orbit are mapping out layering in the crust, ice sheets, and maybe interfaces between rock and frozen or liquid water. As data piles up, we'll get a clearer view of how much liquid is there, how it moves, and how stable it is. Future missions could drill deeper or drop heat probes to directly sample warmer regions. Right now, the verdict on which world is more habitable below the surface is still open. Mars is closer and easier to study in detail, but might be more limited over time. Titan is farther and harder to probe, but could hide a huge, long-lived volume of slushy, life-friendly zones under its ice. That uncertainty is not a side note, it's the core tension, because it means every mission choice you make today is, in a way, picking which mystery you're going to solve first. And remember, even if the interiors of Mars and Titan are both promising, you still have to actually get machines down onto their surfaces safely before you can investigate anything in detail. So the next big question is simple and brutal. When you're screaming into the atmosphere at several kilometers per second, do you want Mars's thin air that barely catches you, or Titan's thick haze that slows you down over hours but hits you with cold and complexity in a different way? Here's the next thing you have to face. When you slam a spacecraft into another world at several kilometers per second, which nightmare do you pick? Mars's short, violent plunge, or Titan's long, cold fall? Mars first. Every big Mars landing you've heard about goes through the same basic pattern. The spacecraft hits the top of the atmosphere at something like 5 to 7 kilometers per second, around 11,000 to 15,000 miles per hour. That's hypersonic. The thin carbon dioxide atmosphere is just thick enough that you get brutal heating on the heat shield, so you need serious thermal protection. But it's still too thin to slow you down gently with parachutes alone. So you come in, you ride the plasma, you deploy a supersonic parachute to bleed off speed, then you still have to fire descent rockets in the last phase to keep from smashing into the ground. That's why missions like Curiosity and Perseverance used the Sky Crane system. The main descent stage fired rockets while hovering, then lowered the rover on cables, then flew itself away to crash at a safe distance when it was done. All of that had to run automatically in about 7 minutes, with no real-time control from Earth because of the light speed delay. If anything big goes wrong during that window, the mission is over. The atmosphere on Mars is thick enough to make entry hard, too thin to make landing easy. You get heat and stress at the same time. Now compare that to Titan, where the profile is almost the opposite in timing. The Huygens probe entered Titan's atmosphere in January 2005. From the top of the atmosphere down to the surface, the descent took about 2 hours and 27 minutes. Not 7 minutes, more than 2 hours. Titan's air is dense. The surface pressure is around 1.5 times Earth's. That means parachutes actually work very well. Huygens deployed a series of parachutes, slowed down steadily, and had time to measure winds, haze, and clouds all the way down. Instead of a single compressed terror window, you get a long, slow fall. That doesn't mean Titan is easy, it means the failure modes change. On Mars, if a parachute doesn't open correctly or a radar altimeter misreads, you crash before you can react. On Titan, you have to survive for hours in a freezing, chemically active atmosphere, with electronics staying warm, parachutes stable in possibly shifting winds, and instruments operating the whole way. You have more time to gather data, but also more time for something subtle to go wrong. Then there's the thermal part. On Mars, the heating is short, sharp, and extreme. You slam into thin air at high speed, the heat shield takes a big, intense pulse of energy, and then it's over. The outer surface gets very hot, the inner structure has to survive that spike, but the environment beyond the shock layer is still extremely cold and low pressure. The whole entry event is like a punch, hard and fast. In Titan, the heating is more spread out. The atmosphere is thick and deep and gravity is lower. You still have to dump a huge amount of kinetic energy, but you do it over a longer distance and a longer time. The exterior of your spacecraft sees a weird combination: extreme cold during cruise, then rising temperatures and aerodynamic heating during peak deceleration, then back to cold conditions as you descend slowly toward the surface. You have to build hardware that doesn't crack at cryogenic temperatures, but also doesn't fail under heating loads. The materials and design have to survive both ends of the temperature range in one mission. And even if you nail the entry and descent, you're not done. The last few meters matter, and they look very different on Mars and Titan. On Mars, landers worry about rocks, slopes, and dust. You don't want to land on a boulder or on the side of a steep crater wall. You aim for relatively flat plains, and you still need hazard detection in some missions to avoid large rocks and trenches. The soil is dry, dusty, and sometimes cemented into harder layers. If your landing gear is weak, you can tip, sink in, or damage instruments when you hit. So, landing on Mars is about avoiding hard obstacles and making sure the ground can support your weight. On Titan, the surface risk shifts. The ground can be soft organic grains, like very cold sand made of complex hydrocarbons, maybe mixed with ices. There can be areas that are more like mud, where liquids have flowed and soaked the surface. There can be puddles or shallow pools of liquid methane. There are also real lakes and seas that you absolutely do not want to splash into unless you built a floating probe on purpose. Huygens landed on a surface that, from its data, behaved somewhere between damp sand and clay. It compressed a bit, it didn't bounce like on bare ice or rock, and the instruments saw signs that the ground might have been moist or coated with a thin liquid layer. So for Titan landers, you have to design legs and bodies that can deal with a range of soft surfaces, maybe partial submersion, maybe slow sinking. You have to think about what happens if you come down at the edge of a flooded region, or in a depression where liquids gather. It's less about rocks, more about softness and liquids. Once you're on the ground, the two worlds split even more when it comes to what you can do in the air. On Mars, aerial mobility is barely possible. The Ingenuity helicopter pulled it off, but it has huge, lightweight blades spinning very fast, holding up a small mass in very thin air. It can only fly in short bursts, and every flight is a huge engineering achievement. Scaling that up to big cargo drones or human vehicles is extremely hard. Mars pushes you toward rovers wheeling across the ground, slowly. On Titan, that calculation flips. The low gravity and dense atmosphere make flying not just possible, but efficient. Lift is easy. That's exactly why Dragonfly is designed as a rotorcraft. It will take off, fly at a few meters per second, and travel tens of kilometers over the surface between landing sites in one Titan day. For the same power, you can move much more mass than you could on Mars. When you think about a future Titan outpost, you don't imagine convoys of slow trucks. You imagine rotorcraft and possibly blimps lifting equipment and samples through the atmosphere, hopping from one site to another, while rovers handle fine-scale surface work. So Mars gives you a clear, short landing sequence followed by mostly ground-bound exploration with small experimental helicopters. Titan gives you a long descent you can instrument in detail, followed by an environment where flying is one of the easiest ways to get around. Both are dangerous, just in different ways. But even if you can get down safely and move around efficiently, you hit the next big question immediately. Once you're sitting on the ground, what can you actually live off? What can you breathe, drink, build with, and burn using local resources instead of shipping everything from Earth? Here's the next hard question you have to answer once you actually land somewhere. Can you live off the land, or are you basically camping forever on supplies from Earth? Start with Mars, because this is where a lot of serious plans already exist. Mars has two big things you care about right away: a carbon dioxide atmosphere and water ice in the ground and at the poles. The air is thin, but it's almost all CO2, which is a good raw material. With enough electrical power, you can run a reaction where you take CO2 from the air and hydrogen from somewhere else and turn them into methane and water. Then you split that water into oxygen and hydrogen. In plain language, you use electricity to rearrange atoms so that carbon and hydrogen become fuel and oxygen becomes your oxidizer and part of your breathing mix. This is exactly what Starship-style Mars architectures talk about. You land with some hardware, you scoop CO2 from the air, you grab water rights from the ground, you run the chemistry, and you end up with tanks full of methane and oxygen for rockets, plus water and air for the base. It's not easy. You need big reactors or a lot of solar panels, compressors, pumps, and systems that can run for months without failing. But the chemistry itself is well understood. You're not inventing new reactions. You're just scaling up industrial processes we already use on Earth. Water ice on Mars also covers the basics. You can melt it to get drinking water. You can clean it and use it for agriculture inside sealed habitats. You can split it into hydrogen and oxygen for fuel and air. Ice in the soil also acts as construction resource because you can mix it with regolith to make concrete-like materials. So Mars gives you a clear path. Pull atmosphere and ice into machines and push out fuel, air, and building materials. Now put that next to Titan. Titan skips one of those steps entirely. You don't have to synthesize hydrocarbon fuel there. The methane and ethane are already in liquid form on the surface, in lakes and seas and maybe underground reservoirs. It's like landing on a world where natural gas has pooled at ground level. From an energy perspective, that's huge. Instead of starting with CO2 and building fuel, you start with fully formed fuel molecules. Your job is to pump, refine, and store them safely at cryogenic temperatures. The hard part on Titan is the other side of the fire triangle. You barely have any free oxygen. To burn methane for energy or use it as rocket propellant, you need oxidizer. That has to come from splitting water ice or importing oxidizer from elsewhere. So it flips the Mars situation. On Mars, fuel is work and oxidizer is work, but both are available through chemistry with air and ice. On Titan, fuel is easy, oxidizer is the limit. Power is also tight because sunlight is basically gone, so you lean hard on nuclear. But once you have those reactors and oxygen plants running, you're sitting on a near infinite fuel source for human standards. Then think about what you build your homes and tunnels out of. On Mars, the ground is basaltic regolith, basically crushed volcanic rock. You can use it to make bricks, concrete-like mixes, ceramics, and if you go all in, you can smelt metals from it using large amounts of energy. You can 3D print structures using regolith-based binders. You have rock for shielding and foundations, and you have ice as a reinforcing component or as a core you cover with regolith. So the base materials are similar to a cold, rocky desert on Earth, just drier and more extreme. On Titan looks strange, but it also gives you a lot to work with. At Titan's surface temperature, water ice is as hard as rock. You can dig it, cut it, and stack it like stone. On top of that, you have huge deposits of organic solids, the dark material sometimes called tholins, produced by the atmosphere and rained down over long periods. You also have frozen hydrocarbons and other organics. That means you can think about icecrete, mixtures of ice and fibers or organics 3D printed into walls and domes. You can use frozen hydrocarbons as plastic-like structural elements and insulation. For radiation shielding and micrometeorite protection, you can pack thick layers of ice and organic grains around your habitats. In other words, Titan is weird, but it isn't empty. It's rich in carbon-based solids that are basically ready-made feedstock for construction, once you design machines that can work at that cold. Now look at the air itself as part of your resource map. On Mars, the atmosphere is very thin, but it's still useful. You can compress CO2 into tanks and feed it into reactors and greenhouses. You can strip out the small amounts of nitrogen and argon for life support gas mixes, so you're not just filling habitats with pure oxygen, which is dangerous. The air is a working fluid for radiators and some machines, even if it's not dense. So you treat the atmosphere as a low-density source of carbon and as a convenient reservoir for industrial processes. Titan's atmosphere is a different level. It's dense, and it's made mostly of nitrogen with some methane. Nitrogen is one of the key elements for life, and on Earth, it's a limiting nutrient in many ecosystems. On Titan, the whole sky is nitrogen. That gives you massive supplies for making fertilizers, life support gas mixes, and industrial chemicals. The methane portion of the air feeds directly into your fuel and plastics chain. You can literally scoop atmosphere and turn it into products. The atmosphere isn't just a background, it's a working stockpile of nitrogen and carbon you can tap continuously. So when you zoom out and think like an economist instead of just an explorer, the story becomes pretty clear. Mars functions as a training ground for using what's already there, what people call in situ resource utilization. You learn how to pull CO2 from thin air, dig and melt ice, build with regolith, and close your life support loops. You develop the hardware, the repair knowledge, and the operational discipline for living off local resources instead of shipping everything across tens of millions of kilometers. Titan is not a training ground. Titan is what you graduate to when you want a full industrial playground. It's farther, it's darker, it demands nuclear power from day one. But in exchange, it offers abundant carbon, hydrogen, and nitrogen, all in forms you can access with pumps, drills, and refineries rather than with deep mining or complex synthesis. For civilization thinking in terms of manufacturing, fuels, long-term chemical industries, and maybe even export of propellants to other outer system locations, Titan starts to look like the big prize. So the question gets sharper again. Do you invest first in the nearby world that lets you practice resource use in a relatively forgiving setting, or do you dream long-term about the distant moon that could power a whole outer system economy once you're strong enough to get there? And underneath that, there's another layer you can't ignore. We're talking like all of this is a clean choice, but our decisions are already biased by where we've actually been and what we've actually flown. So before you decide which world should come first, you have to ask something simple. Where have we really gone so far? What have we actually landed on Mars and Titan, and how does that history lock in our next moves? So before you argue about where we should go next, you need to face a basic question. Where have we actually proved we can operate already, and where are we still almost blind? Mars is clearly the busy neighborhood. We've been sending hardware there for decades. You've got the early Viking landers in the 1970s doing the first biology experiments on another planet. Then Pathfinder with the Sojourner rover. Then the big wave of modern missions, Spirit and Opportunity exploring opposite sides of the planet, Curiosity, the nuclear-powered rover, Perseverance with its sample caching system, plus the tiny Ingenuity helicopter. On top of that, there are orbiters from NASA, ESA, India, and others, constantly mapping the surface, measuring the atmosphere, and acting as relay stations. Some rovers have driven tens of kilometers over many years, climbing hills, crossing dunes, drilling into rock, and even firing laser pulses to analyze chemistry. By now, Mars is not a mystery dot. It's a world with named craters, detailed maps, and known hazards. That record matters. Every successful landing teaches you what works and what doesn't. Every failure, like missions that crashed or lost contact, teaches you too. We've tested entry, descent, and landing sequences multiple times. We've watched how dust builds up on solar panels, how temperatures swing, how electronics age in the radiation environment. When someone says we're planning a new Mars rover, they are building on a deep stack of experience. The risk is still real, but it's not guesswork anymore. It's a place where we know enough to plan, test, simulate, and be mostly right. Now look at Titan and count. You get one big campaign, Cassini-Huygens, and that's it. Cassini orbited Saturn for over a decade and used repeated flybys of Titan to map its surface with radar, study its atmosphere, and track its gravity. Each flyby was like a partial scan, building up a rough but powerful picture of the moon. Then, in 2005, Huygens detached, hit the atmosphere, and parachuted down to the surface. It sent data for about 90 minutes before its batteries died. 90 minutes on the ground compared to years on Mars with multiple rovers. In terms of raw data volume, Titan is barely explored compared to Mars, but the impact of that one mission was huge. Before Cassini and Huygens, Titan was basically a fuzzy orange ball in telescope images. After Cassini and Huygens, we knew it had lakes, river channels, dunes, a complex atmosphere, and a solid surface that probes can actually land on without sinking or shattering. Titan went from mysterious moon to serious target in one shot. So right now, Mars feels safe in a psychological sense. We have many missions, many maps, many failure cases studied. Titan feels risky because we've only poked it once. The question is, does that history justify staying locked onto Mars? Or is it exactly why Titan is where you get the biggest payoff? That's where the next phase comes in. Dragonfly. This is the first dedicated Titan lander since Huygens, and the first rotorcraft designed from the start to fly on another world as its main way of getting around. The plan is simple in outline and brutal in detail. Launch in the late 2020s, cruise for years, arrive at Titan around 2034, enter the atmosphere, land in the equatorial dune fields, and then spend at least 3 years hopping from site to site. Each hop covers tens of kilometers. Each landing is a new lab where it samples the ground, sniffs the air, and measures radiation and weather. If it works, Dragonfly will do something at Titan that we've never done anywhere else: run a mobile chemistry lab in a thick, cold, hydrocarbon-rich atmosphere over multiple terrains. It's like dropping a nuclear-powered drone into a completely alien outback and telling it, go find out how far chemistry has gone toward life without liquid water at room temperature. It's high risk, but the scientific return could be enormous. If that mission finds strongly lifelike chemistry, Titan's status jumps overnight. Put that against Mars again, and you see a clear split in technological readiness. For Mars, we've basically moved past the tutorial level. We know how to get into orbit, we know how to land rovers and heavy landers with complex entry and sky crane systems, we've tested some in situ resource ideas and early hardware, we've run long-duration surface missions through multiple Martian years. None of that means human missions are easy, but the path is visible. You can argue about budgets, but you can't say we don't know how to build the basic systems. For Titan, we've done one entry probe and are about to attempt one big rotorcraft. There's no track record of repeated Titan landings, no long list of here's what failed last time to guide you. Every major step still has a big question mark next to it. That means the risk curve is steeper. You're more likely to run into unknown unknowns. But it also means that the first missions to Titan still have the potential to rewrite entire parts of planetary science. You're not refining details, you're discovering fundamentals. So psychologically, the choice looks like this. Mars is the realistic target, the one space agencies can pitch to the public as the next logical step, backed by decades of previous missions. Titan is the bold bet, the one that asks you to accept huge delays, high upfront costs, and more uncertainty in exchange for potentially massive long-term science and resource returns. If you like analogies, Mars is crossing a known ocean to reach a big new continent. Titan is heading for a frozen, barely mapped region with unclear rewards but incredible possibilities. So that's the real tension you're feeling under all the technical talk. Do we keep following the path of least resistance deeper into a Mars-first strategy, or do we intentionally put some of our effort into the weird, distant moon that could change our whole view of life and long-term settlement? And remember, all of this track record is still about missions that leave, land, explore, transmit, shut down. When you talk about Mars or Titan as future homes, you're flipping the model. You're not asking, can we touch it? You're asking, can we stay there? So the next question is the one that actually hits people in the gut. If you had to live your whole life off Earth, not for a week, not for a mission, but for years, do you pick a base under red dust storms or a warm bubble carved into a Titan's frozen shell? So here's the uncomfortable question you have to ask now. If you had to actually live off Earth, not for a week, not for a mission, but for years, do you pick a base under Martian dust or a warm pocket carved into a Titan's frozen shell? On Mars, long-term bases almost certainly end up underground or buried under a thick regolith. The reason is simple: radiation. The surface dose on Mars is several times higher than Earth's. Stay up top in glass domes and you're slowly cooking your DNA. So you dig. You tunnel into rock, you cover habitats with a couple of meters of soil, or you move into lava tubes. Your neighborhood becomes a network of pressurized corridors and rooms. You step outside in a suit, you come back in, you cycle through airlocks over and over. The day-night rhythm helps you a bit. A Martian day is just 40 minutes longer than an Earth day, so your body clock can adjust. You get sunrises and sunsets that look like a cold desert. Temperatures jump from something like 20 degrees Celsius, about 70 Fahrenheit on a good day, down to around minus 153 Celsius, about minus 225 Fahrenheit at night in some regions. So the outside is still brutal, but visually it's a planet, a horizon, a sky, land stretching out. Your brain recognizes it as a place, even if it's hostile. So Mars bases are basically underground suburbs in a red desert. Does Titan even feel like a place humans can mentally handle, or does it cross into something that feels too alien? On Titan, you're also in pressurized habitats, but the outside conditions are pushed to an extreme. The air is thick, mostly nitrogen. The pressure is about 1.5 bar, but the temperature is around 94 Kelvin, minus 179 Celsius, minus 290 Fahrenheit. You do not step outside without serious heating built into your suit. Water ice is solid like rock. Hydrocarbon snow and grains cover the ground. The sky is permanently hazy and orange. The sun is a tiny, blurred spot, not a bright disk. That means your entire life happens inside warm bubbles, embedded in a cryogenic shell. You can literally use water ice as structural material. Walls can be ice reinforced with fibers and covered with insulation. Outside the habitat, pipes and tanks carry methane, ethane, and nitrogen around like an industrial plant. You're not just living in a base, you're living inside a sealed microcity that is wrapped in something that behaves like a frozen chemical plant. So mentally, what's worse, seeing a familiar sun over a deadly desert, or living in safe warmth surrounded by permanent dim orange twilight and extreme cold? Mars at least gives you something familiar to look at. You have a bluish or dusty sky, a visible sun, rocks, hills, valleys, and dust devils that look like slow, thin whirlwinds. You can imagine standing at a window in a buried habitat looking out through periscopes or cameras at a landscape that, with a bit of imagination, could be a desert in Chile or Arizona, just colder and emptier. That familiarity matters. It gives your brain a reference point, some sense that you haven't completely left the kind of world you evolved for. On Titan, outside views are almost psychological weapons. The sky is dim and orange all the time. The ground is dark, coated in organic material. The sun is weak, like a bright star behind fog. You might not want big physical windows at all. You'd probably rely on cameras and interior displays, where you can adjust brightness and color, or even fake daylight to keep people sane. On the flip side, you know you are under a thick atmospheric shield. You don't have to worry about solar storms and cosmic rays in the same way. That could make people feel safer, even if the environment is more visually oppressive. So if the views are that different, what happens when you have to grow food and keep ecosystems running in both places? On both Mars and Titan, long-term survival needs closed-loop life support. Air, water, and nutrients must cycle over and over. You can't afford to throw anything away. But each world gives you different advantages and headaches. On Mars, you have decent sunlight, about 43% of Earth's, and a day length almost identical to Earth's. That means you can at least imagine using some real sunlight through filters and radiation shields for greenhouses. Maybe you concentrate light with mirrors, run it through protective layers, and let plants see something close to a natural day-night cycle. Radiation and UV are still a problem, so glass has to be thick, or partly buried, or combined with water layers to block harmful wavelengths. You also need nitrogen for fertilizers and air mixtures, and Mars doesn't give you much. You'd have to scrape it from the thin atmosphere or dig it out of the soil in chemical forms. Titan flips that balance. There, sunlight at the surface is about 0.1% of Earth's. For practical farming, that might as well be zero. You will run agriculture almost entirely on artificial lighting, powered by nuclear reactors. LED arrays or other advanced light sources bathe your crops in exactly tuned spectra and timing. The advantage is control. You can run 16-hour days, adjust colors for different growth stages, and stack farms vertically. The disadvantage is if your power drops, your entire food system is at risk. But chemically, Titan is very generous. The atmosphere is mostly nitrogen, a critical element for plant growth, and you have carbon everywhere in hydrocarbons and organics. You can make fertilizers and soil analogs more easily once your chemical industry is running. So for ecosystems, Mars gives you easier light and harder nutrients. Titan gives you easy nitrogen and carbon, but forces everything under artificial lamps. Which one you prefer depends on how confident you are in your long-term power systems. All of this loops back into the big strategic fork. Do you try to change the planet to fit you, or do you accept the planet as it is and change yourself and your tech instead? Mars has always been at the center of terraforming talk. The idea is simple to say and insanely hard to do. Warm the planet, thicken the atmosphere, release CO2 from the soil and polar caps, melt enough ice to create lakes and maybe shallow seas. Over centuries or longer, you try to turn Mars into a place where, at least in some regions, humans could walk outside in a light suit, or maybe eventually with no suit at all. Whether it's actually achievable is a huge open question, but the concept lines up with our instinct to fix the environment. Titan does not fit that fantasy at all. It's too cold, too far from the sun, and its whole chemistry is built around that cold. Terraforming Titan into something like Earth is basically off the table. You're not turning liquid methane seas into liquid water seas under a blue sky without rewriting the whole energy budget of the outer solar system. So with Titan, the only realistic path is adaptation. You build habitats and industries that respect the external conditions. You accept that outside will always be lethal, always dark, always strange. You put your effort into better suits, better reactors, better closed-loop systems, not into trying to fix the moon. That's a bigger philosophical decision than it sounds. Mars is where we project our urge to remake another world in our image. Titan is where we accept that sometimes you live inside the machine you build, and the outside stays alien forever. And underneath all the engineering and psychology, there's a deeper ethical problem waiting. When you build long-term habitats on either Mars or Titan, you're not just choosing a tough environment, you're choosing which potential alien laboratory you're going to disturb first. So the next question is sharp. If both worlds might host past life, present microbes, or future prebiotic chemistry, which one do you have the right to touch and how hard? So now you hit the question that makes a lot of people uncomfortable. When you go to another world, are you exploring it, or are you breaking an experiment the universe has been running for billions of years? Start with Mars. The core ethical issue there is simple to say. Did life ever start on Mars at all? We're not talking about forests and animals. We're talking microfossils in ancient rocks, or tiny microbes hiding in subsurface brines. If Mars once had thick air, liquid water on the surface, and active volcanism, it had the right basic ingredients. If life ever got going, even at a microbial level, some traces might still be there, buried and protected. That's why planetary protection rules exist. Space agencies already treat some Martian regions as special. Places where there might be liquid water, even temporarily, are locked down. You can't just drop a dirty lander full of spores onto a location that might host native life or preserve ancient biosignatures. Hardware going to those zones has to be sterilized to strict standards. The idea is you don't want to confuse future science by seeding Earth life onto Mars before you've even figured out if anything Martian is there to study. Now think about what happens if we find clear signs of past life, or, even more serious, simple living cells in a Martian aquifer. We then have to decide how much we're willing to disrupt that biosphere. Do we fence off whole regions as protected parks? Do we limit colonization to areas far from any detected life? Or do we decide that our need for a second home matters more than preserving a tiny native ecosystem in a few underground pockets? There isn't a clean answer. Any large-scale colonization, with humans constantly shedding microbes, is going to contaminate the planet over time. The only real debate is about how fast and how uncontrolled that contamination is. Now, flip to Titan, because the ethical question there is even more unsettling. On Titan, we might not be protecting existing life at all. We might be protecting a future biosphere that hasn't fully appeared yet. Titan's surface and atmosphere are full of complex organic chemistry. You have nitrogen, methane, hydrocarbons, thick haze, and possibly slushy or liquid water pockets deep down. If Dragonfly and follow-up missions find very complex molecules and clear prebiotic pathways, but no evidence of actual life, what does that mean? It means Titan is not just another dead rock. It could be a world partway along the road to biology, a place where the steps before life are happening slowly over millions or billions of years. So the question becomes brutal. Do we have the right to dump Earth microbes into that environment and overwrite that process? If you land unsterilized equipment, leak tiny amounts of liquid water and heat, and eventually put down human bases, you're creating warm, wet, nutrient-rich pockets on a world that didn't have them before. Earth microbes love that. They could grab those niches and start to spread, at least locally. Over very long timescales, they might interact with Titan's chemistry in ways that completely change the natural path it would have taken. In other words, when you colonize Titan, you might not just be disturbing a fragile present ecosystem. You might be shutting down a natural experiment on how life could start in a hydrocarbon world. That's not just a local impact. That hits our entire understanding of how common life could be in the universe. So you have different ethical shapes on each world, and you need to be honest about them. Which one is easier to contaminate? Paradoxically, Titan's extreme cold might slow everything down. Most Earth microbes are not built to operate at 94 Kelvin. Their membranes, enzymes, and DNA simply don't function at those temperatures. So in the short term, contamination might be less explosive. A lot of spores and cells will just sit there, inert. But inert now is not the same as safe forever. Over geological timescales, some fraction of those organisms or their genetic material could get transported into warmer pockets like slushy interior regions or areas around heat-generating reactors and waste systems in a Titan base. There they might adapt, mutate, or exchange DNA in unpredictable ways. So the risk on Titan is long-term, slow, and potentially subtle, but not zero. Mars is warmer in some regions, and it has brines that can stay liquid at very low temperatures thanks to salts. Some Earth microbes and spores can handle those conditions, especially if they're shielded from radiation. If life already exists there, Earth organisms might outcompete native microbes, swap genes with them, or just confuse the signal so badly that you can't tell what is Martian and what is imported. In that sense, contamination on Mars is more likely to be active and noticeable on human timescales, while Titan's contamination risk is more stretched out, but possibly deeper. Now, tie that to the order of operations. The choice of which world you seriously develop first doesn't just change engineering timelines, it changes the story of how we learn about life. If you go hard on Mars colonization, build large bases and start serious terraforming attempts, and then, decades in, discover robust native microbes, you face an ugly realization. Earth bacteria and fungi will already be everywhere you've worked. The clean before and after comparison is gone. You might never know what that biosphere would have looked like without you. If you instead rush to exploit Titan's hydrocarbons, building refineries, drilling into lake beds, and venting industrial waste as heat and byproducts before you fully map out its prebiotic chemistry, you risk hijacking the natural path that chemistry was taking. Complex molecules that would have slowly evolved under Titan's own rules now get mixed with Earth life byproducts, alien conditions, and mechanical disturbances. The long, slow experiment gets cut off in the middle. So when people talk about Mars or Titan and treat it like a budget decision, they're missing the real weight. It's not just about money and rocket design. It's about deciding whether you prioritize science or settlement, and which alien lab you're willing to disturb first to keep your own species safer. That's the line you can't dodge here. Picking Mars or Titan first is not a neutral step. It's a statement about what you value more, a fast, practical route to a backup home, or a careful, patient approach to understanding how life might arise in very different environments. And under all that ethical weight, you still have to deal with economics. It doesn't matter how interesting Titan is if no one will pay for it. So the next question is harsh but unavoidable. When leaders are looking at cost per kilogram, launch windows, and election cycles, does Titan ever really stand a chance against Mars? Here's the next blunt question you have to face. Even if Titan is cooler scientifically, does it ever win in a world where every kilogram to space has a price tag? Start with cost per kilogram, because rockets don't care about dreams, they care about delta V. Every extra kilometer per second of speed you need increases your fuel mass and your launch mass in a non-linear way. You don't pay a little more, you pay a lot more. Getting from low Earth orbit onto a path to Mars takes on the order of a few kilometers per second of extra delta V. Getting onto a path to Saturn and Titan takes closer to 6 kilometers per second beyond low Earth orbit. That doesn't sound huge when you just say the numbers, but for rockets, it's a massive jump. That's why a mission like Dragonfly, which is just a rotorcraft and carrier, already sits in the multi-billion-dollar range for total life cycle cost. One robot, one destination, and one arrival in the 2030s. Price tag in the billions of dollars. Now scale that up in your head to a crewed mission to the Saturn system. You'd need heavy life support, shielding, large reactors, landers, ascent vehicles, and redundancy everywhere for a journey that lasts years each way. The cost isn't double or triple a Mars mission, it's potentially an order of magnitude higher. So on raw economics, Titan starts to race with a weight tied to its ankle. Then look at mission cadence, because public interests run on calendars, not on orbital mechanics alone. Mars gives you launch windows roughly every 26 months. That means every 2 years and a bit, you get a chance to send something. You can plan a sequence: orbiter now, rover later, sample return after that, and a possible crewed mission after another cycle. You can show progress on a timescale that fits career lengths and public attention spans. Titan doesn't work like that. To get to Saturn efficiently, you often need gravity assists, long cruise times, and very specific alignments. Each mission is a multi-decade project. Cassini took about 7 years to get to Saturn, then operated for over a decade. Dragonfly will take years just to arrive. So from approved to first real results, you're talking a big fraction of a human working life. That's harder to sell to voters and funding agencies. Mars lets you say, we'll launch this in 5 years and land in 6 or 7. Titan makes you say, your kids or your successors will see the main science phase. So if mission cadence and cost both favor Mars, why talk about Titan at all? Because of how infrastructure stacks. When you invest in a Mars program, a lot of the technology overlaps with things you need for the Moon, for near-Earth asteroids, and for deep space operations closer in. Heavy launch vehicles, in-space refueling, life support systems, radiation shielding, surface habitats, rovers, ISRU plants using ice and CO2, all of that is directly useful in cislunar space and the inner solar system. A Mars-first strategy reinforces a broader space economy near Earth. You build depots in Earth orbit, stations around the Moon, mining operations on asteroids, and use similar systems across all of them. Titan taps a different tech tree. A Titan program leans heavily on things like very long-duration cruise stages, high-reliability nuclear power, advanced autonomy for robots that must operate with more than an hour of signal delay, and extreme cryogenic engineering. That's incredibly valuable, but it's further down the line. Those capabilities become really important once you're already comfortable operating far beyond Mars, sending fleets of probes to the outer planets, maybe building infrastructure in the Jovian or Saturnian systems. In other words, Mars fits the next step from the Moon. Titan fits, we already live and work in deep space all over the place. Now look at return on investment from 2 angles: science and settlement. Scientifically, Titan is very high leverage. One well-designed flagship mission can completely change your understanding of organic chemistry, atmospheric processes, surface interior interactions, and the possibilities for life in non-water solvents. A handful of lander sites can give you a cross-section through dune fields, impact areas, and maybe places where liquid and solid phases mix in interesting ways. You could end up rewriting whole chapters of planetary science and origin of life theories off a single mission that works well. Mars science is also strong, but we're already in the details and confirmation phase. We are hunting for specific signs of past life, refining climate history models, and preparing for sample return. That's essential work, but each new mission tends to extend and refine rather than completely overturn the picture. So in pure, wow, we just learned something nobody expected terms, Titan might give you the bigger punch per mission. For settlement and near-term strategy, Mars wins. A Mars program pays off earlier in the form of human-rated systems, surface operations experience, and technologies you can reuse on the Moon and near-Earth asteroids. It might unlock early industrial activity like mining water for propellant, building large structures in low gravity, and eventually exporting some products back toward Earth or outward toward the asteroid belt. Those are tangible economic and strategic returns on a timescale of decades. So you end up with a split. If your horizon is 20 to 50 years and your job is to make sure your country or your company gains useful capabilities and experience, Mars is the rational call. If you zoom out and imagine a civilization that has already mastered nuclear power in space, autonomous robotics at huge distances, and large-scale space infrastructure, then Titan looks less like a wild side quest and more like an anchor point for the far future. And that leads straight into the next question, maybe the most important one in practical terms, given how our technology actually move. What does the next 100 years really look like? Mars first, Titan later, or something stranger? In the near term, say the 2020s through the 2040s, Mars is clearly in the lead. That's not a guess. That's just following the hardware that already exists or is on the drawing board. You can expect more orbiters refining maps, more landers testing specific instruments, and more rovers crawling around, drilling rocks, and caching samples. Mars Sample Return will probably be the big flagship project of this window, bringing pieces of Mars back to Earth labs for deep analysis. If commercial plans and national space programs line up, there's a real chance you see the first crewed missions to orbit Mars or even land on the surface before mid-century. All the early demos happen there. Life detection instruments, ISRU prototypes that pull oxygen out of the air or water out of the ground, habitat tests, maybe even early greenhouses. Long before we do anything comparable on Titan, we'll be running experiments on Mars that directly answer, can humans live here for more than a few weeks without everything falling apart? So where does Titan fit into that same time window? Is it just sitting in the background, or does anything real actually happen? Titan's big moment in that time frame is Dragonfly. If the launch stays on track and the cruise goes well, it shows up around 2034. Then you get at least 3 years where this rotorcraft is hopping tens to hundreds of kilometers across Titan's surface. It hits dunes, impact sites, and maybe regions where liquid and solid have interacted, and it samples organics and ices at each stop. That data is going to be intense because it's the first time we've flown a mobile lab in an environment like that. Over that period, Titan either stays interesting but niche, or it flips to priority target. If Dragonfly finds strong prebiotic chemistry or even hints of weird lifelike processes, Titan gets bumped way up the list for future flagship missions. So in the 2030s and early 2040s, Mars dominates in volume of missions, but Titan might grab the headlines if the chemistry story is big enough. Push forward into the medium term, the 2050s up to around 2100, and the paths for the two worlds really split. If everything goes even moderately well, first human footprints on Mars are plausible before mid-century. Once you land people once, the pressure to go back is huge. You'll get more missions, more permanent bases, more industry. By the late 21st century, you could see semi-permanent habitats, rotating crews, maybe even a small long-term community. You'd have local production of propellant, oxygen, water, and building materials. Mars becomes an actual human place, not just a robot park. Now be honest, do you see humans on Titan in that same window? Realistically, no. A crewed Titan mission before 2100 would be almost science fiction level aggressive. The trip takes years each way, the energy cost is massive, and the life support systems you'd need are way beyond anything we're even sketching seriously right now. So in that time frame, what do you actually expect for Titan? More robots. Follow-on orbiters that map gravity and interior structure better. Maybe a dedicated ocean or slush probe concept. Landers aimed at lakeshores, dune interiors, or cryovolcanic regions. If Dragonfly's results are strong, you might even see proposals for submersible probes in the methane lakes, designed to swim and sample those alien seas. So while Mars is arguing about how many people live at Base 3, Titan is still in the robotic exploration phase, but with much better coverage than today. Now jump even further, past 2100, into the 22nd century and beyond. You're in speculation territory, but you can still reason it through. If human civilization holds together, avoids wiping itself out, and keeps investing in space, a few things probably become real. We'll get much better at nuclear fission in space, and maybe crack practical fusion. We'll have large-scale infrastructure in cislunar space, around Mars, and probably in the asteroid belt. At that point, the outer solar system starts to look less like too far and more like the next industrial zone. In that era, Titan's profile changes. Suddenly, a world with abundant hydrocarbons, nitrogen, and possible interior water stops being a curiosity and starts looking like a strategic asset. For a civilization that isn't relying on direct sunlight for power anymore, because it has fusion or huge fission fleets, being 10 times farther from the sun isn't a big deal. You can stick reactors on Titan, pump hydrocarbons, crack ices, and use that stuff locally or ship it around the Saturn system. Titan could become a hub for outer system industry, science, and maybe, eventually, very heavily supported human habitats or rotating stations in Titan orbit that use the moon as a resource base. So when you line it up this way, what are you actually choosing when you say Mars first or Titan later? You're not just picking locations, you're picking chapters of a story. Mars is the next chapter. It's the one that realistically plays out over the next 20 to 80 years. More robots, then humans, then bases, then early industry. It's the extension of what we're already doing with the moon and low Earth orbit. The tools, the budgets, they all fit into this near-term Mars narrative. Titan is the chapter after that. It's the part of the story where the genre shifts from classic space exploration to outer system civilization. That's when energy comes mostly from reactors, not sunlight, when robots do most of the frontline work, and when humans, if they go at all, are supported by massive, mature infrastructure. Titan is where you go when being a planetary species isn't enough anymore, and you're actually acting like a multi-world civilization. So the timeline answer is harsh and clear. In your lifetime, or your children's, Mars will always be in front. Titan will be a place we visit with robots and argue about in science conferences. In your grandchildren's or great-grandchildren's timeline, if things go well, Titan might turn from an orange dot with a few lander tracks into a key node of human activity far from the sun. Which brings you back to the question you started with. Now that you've seen the physics, the chemistry, the habitats, the ethics, and the timeline, what's the honest verdict? Should we go to Titan instead of Mars? Should we stick to Mars? Or are we thinking about this whole choice the wrong way? So after all of that, here's the real question you've been dancing around the whole time. If you had to pick, right now, do you send humanity to Mars or do you aim straight for Titan? Start with the most brutally honest filter, speed. How fast do you actually want to see humans standing on another world? If your goal is speed, Mars wins, and it's not even close. The trip is months, not years. The launch windows come around every 26 months, not once in a lifetime. Sunlight at Mars is weak but usable, around 43% of what Earth gets. Solar panels actually work there, at a few hundred watts per square meter instead of a few tenths of a watt like on Titan's surface. We already have working entry, descent, and landing systems for rovers that weigh as much as a small car. We've tested some of the chemistry for making fuel from Martian air and ice. If you want to see humans walk on another planet while you're still alive, Mars is the sane, boring, practical answer. Trying to do that on Titan with current or near-term tech would be insane. You'd need to survive 7+ years of deep space cruise, brutal Delta V, cryogenic conditions, and then operate in an environment where solar power is basically zero, and everything depends on nuclear reactors. So in terms of humans there quickly, Titan isn't in the same league. Mars takes that round. But is speed actually the thing you care about most, or are you more interested in what gives you the biggest upgrade in our understanding of the universe? If your main goal is science, especially about life and chemistry, Titan might be quietly the better pick. Look at what it hands you just by existing. You get a thick nitrogen atmosphere that shields radiation and keeps complex molecules stable on the surface. You get active methane weather, real clouds and rain, lakes and seas of liquid methane and ethane that have been filling and evaporating for who knows how long. You get surface organics that don't cleanly fit into our Earth-based rules, structures and reactions that mess with the like dissolves like idea you learned in school. On top of that, you probably get layered interior with slushy or even liquid water and ammonia in deep pockets, potentially hitting temperatures around 20 degrees Celsius, about 68 Fahrenheit, in some zones. That's easily in the comfort range for life as we know it. Now stack all of that next to Dragonfly. If that rotorcraft lands, flies, and starts sampling chemistry, and it finds complex prebiotic chemistry, things that look like they're walking right up to the edge of life but haven't crossed it yet, Titan jumps straight to the top of every astrobiology list. It becomes the place you have to keep going back to because it's running a live experiment on how far can chemistry go without Earth-like oceans. So Mars can absolutely deliver huge results too, especially if we find past life or present microbes underground. But in terms of wild alien chemistry that challenges our intuition, Titan has more knobs to turn. So for pure scientific shock value, Titan has a real shot at beating Mars. But science and speed are still short to medium-term goals. What if you zoom out and ask a colder question? Which world actually looks better as a long-term base for a civilization that isn't tied to sunlight and isn't scared of nuclear power? If your goal is long-term civilization, Titan becomes this strange, dark favorite. Look at its resource profile as if you're planning for centuries, not decades. You get a thick atmosphere that takes care of radiation shielding for you, so you don't have to bury every habitat under meters of rock. You get enormous quantities of hydrocarbons, essentially a natural gas world, sitting as liquids in lakes and soaked into the ground. You get an atmosphere made mostly of nitrogen, which is gold for life support and agriculture. And you probably have water ice and internal slush layers that can be tapped for water and oxygen once you have enough power to drill and melt. If your civilization has fusion or advanced fission reactors, and if you're not relying on direct sunlight anymore, Titan starts to look like a nearly perfect staging ground in the outer solar system. Dark, yes. Hard, yes. But energy-rich and resource-dense in exactly the elements you need to build complex chemistry, industry, and long-term habitats. Mars is still valuable in that future, but Titan feels like a better hub once you're playing at that scale, especially for civilizations that want to spread through the outer system rather than cling near the sun. So put it all together and answer the title question head-on. Should we go to Titan instead of Mars? The honest answer is no, not instead. Mars should come first. Mars is where we learn how to walk off-world without immediately dying. It's close enough that we can send people, test hardware, fail, fix, and repeat in human timescales. It shares tech with lunar bases and asteroid missions. It gives us a near-term target that can actually be reached and settled with the tools we can realistically build in the next few decades. But if we stop at Mars, if we treat Mars as the final boss and not just the next level, we miss the real twist. Titan is not the next step, it's the step after that. The one that tests whether we're serious about being a spacefaring civilization, not just visitors to a nearby desert. Titan is where you go when you had reactors that run for decades without failure, robots that can operate almost fully on their own, and enough will to invest in missions that might only pay off for your grandchildren. So the smartest path isn't Mars or Titan, it's Mars first, Titan later. Mars is where we prove we can build bases, close life support loops, and survive for years away from Earth. Titan is where we find out whether life itself was ever limited to Earth in the first place. So don't just pick one world over the other. Ask yourself which future you're willing to build, the near-term Mars era or the deeper, stranger Titan era that might come after it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.